Alright, so let's measure capacitance using this keysight meter. First of all, let's just do the lead resistance, just so we have a good idea of what the lead resistance is. 0.06 ohms. Not that it's going to do much because this is not measuring ESR, but just to show that it's a pretty low impedance set of leads. And hopefully not contributing too much to the ESR. So let's look at capacitance. .12 microfarads. So that's a pretty good measurement. And over onto the polymer cap. .958 microfarads. So let's check out some other meters. We will be hooking up the scope to these things in the next round, but for now we're just measuring capacitance. So multi-layer ceramic. .19. This is a Vichy VC97 meter. They're all auto-ranging meters, and it takes them a while to lock in on a large capacitor like this. And now let's do the polymer cap. .2 microfarads. Next meter. Actually, we don't need to disconnect it. We'll just plug in the leads. Capacitance. 10.13, pretty similar. And let's look at the multi-layer ceramic. .26 microfarads, or 10.17, somewhere in there. Okay, let's hook up the oscilloscope just to show what the waveform is of these meters when they're measuring capacitance. Okay, this meter has a bit of a weird waveform. It starts at about 0.6 volts and goes up to about 1.1 volt. Every second cycle there's a bit of a half peak in there. But you can clearly see it's a capacitance charge discharge curve. And it's not going near the full charge or full discharge, so that it's still got good discrimination on the level. So if it charges right up to the peak, it would be sort of indeterminate when it got there. But if they stay where the charging cycle has got a high slew rate, they can get better resolution. All right, next meter. So this meter has a consistent waveform using almost exactly the same voltage, about almost 0.6 volts to almost 1.1 volts. And the frequency in both cases is 1.2 hertz. And let's try the key sight. The key sight's completely different. So the key sight looks like it's using a current source. So these charge and discharge cycles are straight lines. So this is a much more expensive meter, and it looks like a more expensive technique. So here we have the frequency is 2.5 hertz, and just expand it out a little bit. At 100 milliseconds per division, we can see that it's a perfect triangle wave, which indicates that they're using a current source to charge and discharge the capacitor. Very nice. So let's look at the peak meter and how it measures capacitance. We can see there's a fancy waveform at the beginning which is measuring the ESR, I think, and then it goes into a steady state capacitance measurement using a linear charge discharge pulse, which is a current source and a current sink, which is a nice waveform. It's only 23 millivolts, which is considerably smaller than the other meters, but it may help it to not matter too much if you've got a polarized capacitor. However, the leads are polarized. We can see that there's a positive 23 millivolts here, and I think I'll put some heat shrink on that lead to make sure I can figure out which is the positive terminal in the future. Now I'm going to see if I can capture the image of the initial ESR test. So I grabbed a shot of the startup of a test, and I set the cursors up. Let's expand this out a bit and move the cursor over. And this little burst in the middle, let's see if we can figure out how long that is. Okay, so let's move this over to the start of that burst. Okay, so this little burst in the middle is 3.887 milliseconds. Let's take a look at the period. Let's go here and move this over to the rising edge of the next pulse. So the delta T between this pulse and that pulse is 34.27 milliseconds. Now let's look at the whole burst. So from this rising edge of the big pulse to the rising edge of that pulse, we have 293.5 milliseconds. And it looks like this pulse goes a little negative, minus 6 millivolts. Interesting waveform. But this meter is doing something quite different to measure ESR from this meter.